Thank you very much, Jim, for your kind words, and also thank you very much for the kind invitation to give a talk here this evening. As Jim told you, I was trained as a physical geographer, specializing in meteorology, climate, glaciers, permafrost, cold climate issues. But I was also trained as a geologist, which gives a good background to take a bigger look on certain issues. So today I'm going to talk a little about what is the situation here in 2024. And I will use observations, real observations on meteorological phenomena. All of these are freely available on the internet, so it's not my own measurement. And I will do this talk on a background of a general question. This one, are we currently in a climate crisis, as you may be led to believe if you follow today's news media? I'll come back to that later. Here's a short outline of what I would like to talk about. A lot of different things, as you can see, so time will not allow me to go into great details with certain issues and for all of these things. But I hope I will be able to display some interesting data, and by comparing some data, you may even get some ideas about useful hypotheses you could use for further work. So I will start off by talking a little about temperatures in the atmosphere, and then talk about the ocean, sea level, sea ice, snow, wind and storms, precipitation, and cloud cover. And then I will do some reflections at the end of my talk. Atmospheric temperature. Here's a graph showing annual temperatures, anomalies. The zero line is calculated at the average of 30 years from 1979 to 2008. I'll show you this, which is a Hadkrut data, simply to illustrate how warm 2023 was. On this record, it was clearly a record holder. And one question, which we'll come back to, could be, why was last year so warm as it turned out to be? Here's another way of looking at last year's temperatures. Here I'm using satellite data on temperatures. And what I did was taking for each location on the planet, the average temperature for 23 and compared with the average for the preceding 10 years, just to get an impression about is this really a serious warming or whatever is going on. And what we see is that even though we have to admit that 23 was a very warm year, it was not extremely warm at all places. It was mainly, I hope, can you actually see when I move my pointer around? I'm pointing to this area in the Pacific Ocean near the equator, where we have El Niño playing out last year. And the colors, the green, yellow colors illustrate that here temperatures are above that last 10 years, the average for the last 10 years, and the blue color illustrate where temperatures was lower than the previous 10 years. And what springs to eye is the warm area in Canada and northwest Russia. But we have to remember this is a Mercator, so-called Mercator card projection. So areas near the equator looks far too small compared to areas near the poles. So, and actually we have about, or exactly 50% of the total surface of the planet located between 30 degrees south and 30 degrees north. And if you take the area of Mexico, it roughly corresponds to the area measured in square kilometers of Greenland, actually. So just to give an impression about how careful you should be with some of these maps. Here's a satellite temperature record since 79 from the lower troposphere, a couple of kilometers above the planet surface. And this illustrates, it goes to April 2024, how high these temperature anomalies are at the moment. And this is because of this oceanographic phenomenon playing out in the Pacific Ocean, El Niño. We have another one playing out in 2016 and a famous one back in 1997-8. So this is what we are seeing just now, and most likely I would be very surprised if temperature is not going to drop back rather quickly during the next 2 or 3 months. Time will show. Here's another temperature record from the Goddard Institute in USA, showing very much the same. There are some differences, of course. But what I would like to draw your attention to here is that although all these people who are making these databases, they're doing a very big job, and we should all be very happy that they're doing this job, then there are some issues which I do not fully understand. One issue is the red line here. The blue line illustrates the last data set, how it looks, was downloaded 1 month ago. Goes until April 2024. And in May 2008, I downloaded the data as well. And this is the red line. And you can see that also data which occurred or describing the situation previous to 2008, they have been changed in the meantime. There's been some general warming in the record. So these databases are not all completely stable. They're exposed to what I call administrative changes, and there are probably many good reasons for this. But when you get a temperature record and you compare it with the same temperature record 1 year later, you should not be surprised if you're getting 2 different results. Here's actually, I did an experiment comparing the record from May 2008 with the most recent record, and there are data going back to 1880, monthly data. And you can see in the meantime, since 2008, the time interval between 1900 up to the Second World War, they have been experienced to cooling, some cooling after the Second World War, and since about 1975, 1980, there's been warming. I picked 2 years, one from a warming period, January 2000, and another year from a cooling period, January 1910, to prepare this diagram so you can see what is happening. The upper curve illustrates month by month how you could download temperature for January 2000 or anomalies, and the same for 1910. So if you compare the 2 months back in May 2008, there was a temperature of warming between these months of 0.45 centigrades. But if you do the same in May 2004, the exactly same month, the temperature warming from 1910 to 2000 has increased to 0.67 centigrades. So this is a quite serious change of data, actually. And as I mentioned, there are probably reasons for this. This was one issue. Another issue which I find interesting in the temperature data records, especially the surface temperature records, it doesn't really apply for the satellite records. It is illustrated by this slide here. This is a measurement I did in Oslo some years ago. Oslo is located in the southern part of Norway, as you all know. On this map here, we have downtown Oslo located about here. I hope you can follow the pointer. And the blue line indicates the route I took in a car where I mounted a temperature sensor on. So I started here northeast of Oslo in open country. It was wintertime, February, arrived into the town, across town, past actually the Meteorological Institute, and then I went into the open terrain northwest of Oslo. And here's the temperature record. When I started, it was, you can see it's late January 2007. The temperature driving through the open country northeast of Oslo was almost down to minus 17 degrees centigrades. Then as soon as I came into the town, temperatures went up. And when I passed the Meteorological Institute, it was about -9 or about 8 degrees higher. And then I went out of Oslo into the open terrain northwest of Oslo, and then temperatures dropped back to somewhere between -15 and -16. This is a nice example of what we could call the urban heat island effect. And I'm not completely convinced that when temperatures records are put together in these databases, sufficient consideration is taken to this. But I know they are taking this into consideration, but I don't know the details about it. But it's interesting. I believe that much is still to be learned about the effect of urban heat islands. Polar regions, sometimes we're told that the heating is enormous near the poles of the planet. And here are two satellite records from the lower troposphere going back to 1979 and ending here April 2024. And we have the Arctic area up here, and in the lower part of the diagram, we have the Antarctic area. And you see there has been warming in the Arctic. There was a step-like warming around 1994 and 5, and then slow warming. And then we had the El Niño back in 2016, and there was a serious effect of that El Niño. Then temperatures dropped a little back, and now with a new El Niño, we see another temperature peak. If you go to the Antarctic, it goes up and down, but I would say it's pretty stable temperatures. So we have warming in the Arctic, no doubt about that, but we have almost no warming, I would say, very stable conditions in the Antarctic. Also, if you compare ground-based stations throughout the Arctic, Fairbanks, Nuuk in Greenland, Akureyri in Iceland, Longyearbyen, Svalbard, Ostrov Dixon in northwest Russia, and Khatanga in northern Siberia, you see warming, but it's especially Longyearbyen and Ostrov Dixon, which are seeing clear warming during the past 20 or 30 years. All the other stations, they do show warming, but not to the same degree, far from. And it looks as if you study stations, ground-based meteorological stations, especially stations which are around or in the neighborhood of the Barents Sea, north of Norway, which are affected by this so-called Arctic warming, which tells me that a guess might be that it has something to do with temperatures in the Barents Sea. Nevertheless, you could say that speaking about temperature, the Arctic is much more complicated than is often communicated. Little about ocean temperatures, and you probably all know the Argo profiling floats, which today it's almost 4,000 floats, an enormous program of floats which are drifting around, using some time at the surface, communicating with the satellites, and then they are dropping into the sea and going down to almost 19 or to about 1,900 meters, and then they come up and do measurements of salinity and temperatures. So it's enormous work to put all these observations, which are not site-specific. They're moving around into a database. So no surprise, you can't expect to get data from the previous months, but you have to wait some years before the data are prepared. But here's an overview diagram showing the temperature conditions average temperature condition from surface down to 1900 meters in all the oceans. And you see in the lower part of the diagram, the global oceans, what are called the global oceans. We see a temperature increase. We also see that perhaps we passed a peak around 2020 or something like that. And we see, if we look more detailed at the oceans around the equator, that the global signal is derived mainly from the oceans around the equator. See a clear temperature increase, and just now we're actually looking into declining temperatures. Once again, what I call the equatorial oceans are a big area between 30 degrees north and 30 degrees south, a very big area. In the north, the Arctic oceans, temperature is actually being declining, and once again, it's an average for all 1900 meters. In the Antarctic, much more stable conditions, a little temperature increase, but we'll come back to that. Then I will show you a diagram, and you can't see the individual numbers. And the reason for showing this diagram is simply to show how complicated it looks to me to be. What we see up here in the topmost part of the diagram are data from the surface, or 2.5 meters depth, starting back in 2004, and the record ends in December 2020. Here we see annual fluctuations very clearly. Here we are at 100 meter steps, 200 meter steps, and so on. And we can actually trace these annual fluctuations down to at least 100 meters, and from a statistical point of view, down to almost 200 meters. But the fluctuations near the surface is clearly much bigger than in the bottom part of the diagram. So the scales are not comparable. But I want to show this diagram because if you look at the deeper data, you can see some slight warming beginning around 2009. And then it actually propagates up from great depths towards more shallow depths. So this diagram shows us, without going into too many details, that the temperature in these uppermost 1900 meters of the ocean are influenced by surface conditions, but actually it looks also as if there are some influence from greater depths than 1900 meters. And we should remember that the oceans are much deeper than 1900 meters, and actually the average depth of the oceans is, I believe, around 3.8 kilometers, and some areas are much deeper than this. So even though this knowledge here is very important, there's probably very much to be learned still. Here we see a diagram showing from surface to the left to 1900 meters to the right for this time interval since 2004 to 2020, how temperature change, net temperature changes has been. And we see the greatest temperature increase is near the surface, but much smaller at greater depths. And actually, if you're taking an average value for these 1900 meters for this time period, the average temperature increase is 0.037 centigrade, which is not extremely much, but it is an increase. If you look at a regional scale, it becomes even more interesting, at least seen with my eyes. Here we have the oceans near the equator, surface to the left, and 1900 meters to the right. And these are net changes in temperature since 2004. Not very much is happening at great depths, even a small cooling around 400 meters. And then we see a clear warming near the surface. The uppermost 100 to 200 meters is warming. Same applies for the Antarctic oceans. But here the Arctic oceans comes out very interesting, because you see the uppermost about 1,400 meters of water has been exposed to quite clear cooling, which may come as a surprise to many people, because we all know that the sea ice, the Arctic sea ice, has been diminishing in the same period. But this is what the data is telling us, and probably nature is trying to learn us something, I guess. But I would say much is still to be learned about the oceans. A few words about sea level. In the last climate change report from 2021, in the physical science basis, diagrams like this was published showing that according to the model future, global sea level will, during the time until about the next turn of the century, increase with about 1.5 meters up to 1 meter, perhaps even more. If you take a look at the satellite measurements of the global sea level, you still see a clear increase. This is what we see here. The satellite measurements goes back to about 1992, and the last data I have is from September 2023. And you see, depending on the time interval you take, these data tend to indicate that on average we are seeing global sea level rise somewhere around 4 millimeters per year, which in the time until the next turn of the century probably will give us around 30 centimeters of sea level rise globally. But what is interesting, if you calculate the annual sea level change 12 months or 10 years, we see there are variations up and down. It's very interesting to see what the future is coming. It's not a linear process. There are variations in this sea level rise. If you do the other thing, which I've liked very much, because if I am going to build a house near the shore, my main interest is what a transitional time sea level gauge nearby will show us, not what the satellites are measuring us. And here I found a station in Denmark, central Denmark, and this is from a geological point of view, a very stable area. It's not going up, it's not going down. Most places on planet Earth are going up or down from geological reasons. But this one happens to be quite stable, same distance to the center of the planet. So if you measure the sea level here, you get quite another result. And the measurements here, they start back in 1897 and continue more than 100 years. And here we see almost linear development of less than 1 millimeter of sea level rise per year. So if you forecast this into the coming 35, 36 years, you will get a sea level rise of less than 10 centimeters. Obviously, very much less than the computer models will tell us. From Oslo in Norway represent quite another location, because many places in Northern Europe, also Ireland and North America, they was exposed to heavy glaciations 20,000 years ago. So up to 1 or 2, or perhaps even 3 kilometers of ice was sitting over Oslo 20,000 years ago. And for that reason, when the ice load disappeared, you get an isostatic response. So Oslo is coming up with more than 3 millimeters per year, even though the ocean might be increasing as well. This number, 3 millimeters per year, refer to the difference between the land surface and the ocean surface. So even if the global ocean is getting more water, Oslo is becoming a more and more dry place. But if you go to the last report on sea levels, the IPCC, they calculated that just around 2020, this will change, and now we will see a sea level rise in Oslo. And this sea level rise, this calculated value, is being used by Norwegian authorities to make planning for how to protect the buildings near the coast. But if you do the opposite, the simple approach of taking a linear extrapolation, you see a sea level decrease going into the next turn of the century. Time will show us what is correct. We now have a time overlap of about 3 years, and it looks as if Oslo is continuing to go up in relation to the sea. But we have to wait a longer time. Few words about sea ice. Most models also indicate that especially the Arctic sea ice will decline very much in the year to come. And depending on the model and the model input, the Arctic Ocean is supposed to be practically ice-free, according to some models, as early as about 2050, but at least when we come to the next turn of the century. What is shown here is September extension of sea ice in the Arctic, and this is because September is a month where the sea ice has the smallest extension in the Arctic. So what I did here was plotted for the past 2 years what was the September extension of sea ice, and this plotting here well above the modeled forecast. So the Arctic sea ice is not behaving completely as the model are forecasting. Here's a diagram showing since 2000 how the Arctic sea ice extension has varied month by month. And you can see in the first part of the period there was a weak decline. It never disappears. Zero is down here. So even at midsummer, there's a good amount of sea ice left in the Arctic. And then it increases. But for the last 2 or 3 years, I've actually seen a very small increase of sea ice. So it doesn't look at the moment as if the Arctic sea ice is going to disappear in the near future. Here's another diagram showing both the Antarctic and the Arctic sea ice, because we have 2 poles, so we also have 2 areas with sea ice. And the red curve indicate the overall development in the Antarctic, and the blue curve indicate the development in the Arctic with the extension of the sea ice. And you see that until around 2015, 2016, another El Niño year, the Arctic sea ice increased in contrast to the Arctic sea ice. But then suddenly, after that, there's been a major decline in the extension of the Antarctic sea ice. I've not myself looked into the details, but I've have read a couple of papers trying to analyze what was happening. And apparently there was some kind of change of wind systems. Sea ice sails around with the wind, which can explain this rapid decline of sea ice. But here we see that it looks, at least for the moment, as if the decline of the Arctic sea ice reached a bottom here, almost at the same time as development change in the Antarctic and began to increase a little again. The lower part of the diagram shows the global sea ice extension, quite stable in the beginning, reflecting the decline in the Arctic and the increase in the Antarctic. And then when things happen in the Antarctic, global sea level goes down here. But interesting to see what the future will bring here. But I believe that there are many surprises yet to be recorded as well. A little about snow. We all know that snow is going to disappear. Snowfalls are just now a thing of the past, a famous sentence. But if you look at the satellite record of Snowcover, here it goes back to 1972. The snow cover extent in the northern hemisphere, I'm showing here, is very stable in the southern hemisphere, mainly controlled by the extension of the Antarctic continent. The big variations are playing out in the northern hemisphere, but you can see it's almost surprisingly stable, actually, the snow cover up here. There are some variations up and down, but very small. And if you take another type of diagram here, looking seasonally, here in the upper part diagram, we have the winter snow cover in the northern hemisphere, the spring snow cover, the summer snow cover, and the fall snow cover here. It looks very stable, actually, to me. From a statistical point of view, you can see it's no change in the wintertime. A small decline in the spring, a small decline in the summer, a small increase during the fall. But the main message to me is that the snow cover is actually rather stable in the northern hemisphere, and for geographical reasons, it's very stable in the southern hemisphere as well. A few words about wind and storms. Here's the diagram showing the energy mobilized by cyclones in the Atlantic basins. And the record goes back to 1850 and ends in 2023. And you can see there's no clear trend, ups and downs, variations, but no linear development. There's actually, now we're speaking about the Atlantic basins. If you do a 4-year analysis, there's very clear variation of 61.5 years. And this is well known from the Atlantic area that many climate-related phenomena, they do vary with a period between 60 and 65 years. It's a well-known period. Landfalling hurricanes in the US, no clear trend, ups and downs. And if you look at both hemispheres, we have the global data here. We have the northern hemisphere here, the southern hemisphere here. We see that most cyclones and storms are playing out in the northern hemisphere, but there's no clear tendency here, ups and downs. And we see, once again, a 4-year analysis would indicate there's an important period about 11.5 years and another one about 3.6 years. 3.6 years is actually also typical for the El Niño variations, if you do analysis on that. A little about precipitation. Here's an average for global precipitation from 1960 and 30 years ahead. And it varies very much from almost zero in desert areas to more than 2 meters in some wet areas. And if you calculate the deviations from the mean value over this observational period, looks like this from 1900 until 2021. Periods where the anomaly is slightly negative, then we have a positive period, negative, dry, wet, dry, wet. Overall, there might be a small tendency to increased values over the time period, but the main phenomenon is that there are big important variations here. In this, it's not a clear pattern actually, but interesting. Few reflections about cloud cover, because precipitation normally comes from clouds. And I looked up in one of my old university textbooks on climatology and found that clouds, the effect of clouds, temperature-wise, climate-wise, is very complicated, warming as well as cooling. But the net effect, according to this book, is if you removed all clouds from planet Earth, at the surface, the planet would gain about 17 watts per square meter and become a warmer place. So the net effect of clouds is cooling. And if you do get your hand on some observations, satellite observations on the cloud cover, as you see here in the upper diagram, going from monthly values from 1982 to June 2019, you see that for the first part of the period until about 2003-4, the cloud cover has actually been decreasing slightly on planet Earth. And then it was rather stable. And then I put into the same diagram the temperature, the satellite measured temperature in the lower troposphere. And you see, at least time-wise, when the period where cloud covers decreases a little, temperature goes up, and when it becomes stable, we come into the famous hiatus, where very little change was. This is an El Niño effect. This is also a Niño effect, and a Niño effect here. Another interesting thing is that if you look at the diagram, it looks as if whenever El Niños are playing out, let's take this nice example here around 1997-8, you can see the annual variations of the cloud cover become smaller. Outside El Niño, it's rather big. Here it becomes smaller. Here in the El Niño 2016, once again, the same happens for some reason. I don't understand it fully, but it's interesting. What I do know is that oceans must be a very important player when it comes to clouds, because oceans are covering about 71% of the planet's surface, and most of the water vapor in the atmosphere must come from the ocean. Here you see over the northern part of the Arctic, or in the Arctic between Svalbard and Northeast Greenland. When the air is blowing across sea ice, there's no clouds. As soon as the air is coming over open water, clouds are forming. So oceans are important. So I put together this diagram here where you see from 1982 to June 2019, once again, the cloud cover variation. And here I found that data for the relative humidity in the troposphere, the upper part of the troposphere, about 9 kilometers altitude. And there's some resemblance. It's not exactly the same, but it looks more or less the same. And then I became even more interested when I saw this graph here, which I put in here, which shows a change in the length of the day in milliseconds. And you can see it's almost, it looks very much like this. So here, the day length is getting slightly longer, meaning that the planet's rotation is going down. Here, it's the planet is speeding slightly up. We are talking about very small fractions of seconds. And then it became more or less stable, the rotational rate here. And at the same time, the cloud cover becomes stable, and the relative humidity in the upper part of the troposphere became stable. I have no fixed explanation telling why it is so, or if it even makes sense. And if one factor varies somewhat like another factor, doesn't tell us that one of the factors is controlling the other. There might be a third factor which are controlling all of them, or it could also be a coincidence. Much is still learned about cloud cover, I guess. Now coming back to the principal overall question, are we in a climate crisis? And this will be, of course, my personal impression. Temperatures, first of all, it's impressive work which are being done with these global temperature data. But in my mind, there are some problems with it. I don't understand all the administrative changes. Maybe issues with the urban heat effect. And interesting enough, Antarctic temperatures remain very stable. Ocean temperatures, much to be learned. Oceans are certainly not boiling, as we have heard. Sea level, I don't believe, based on the data, in a sea level rise 1 meter or more until the next turn of the century, but much less. Sea ice, Arctic sea ice is not disappearing at the moment, and I don't believe we understand fully what controls the extension. Snow cover is quasi stable. Snow cover is not disappearing. Storms, there's a lot of recurrent, perhaps periodic variations, no clear trend in hurricanes. Precipitation, also variations superimposed on a slight upward trend since 1900, which may not be so surprising because that's when we came out of the cold little ice age. So global temperatures went up, ocean temperatures went up, so probably evaporations went up as well. So might not be a big surprise if we had a little more clouds and somewhat more precipitation. And then we have the cloud cover. Declined since 1918, apparently, and one might speculate that this also has some effect on temperatures, both at the surface of the ocean and in the atmosphere. Less clouds, more solar energy coming to the surface. So I would say I'm not very nervous. I don't believe we live in a climate crisis. Then you may want me to say something about CO2, but I wanted to focus on what I believe might be interesting or important in this climate discussion. And I realize that CO2 is indeed very important for life. But in my opinion, it's not very important to understand climatic development. So I didn't talk about that. Final slides. I think we'll come back to all the time that the data, when you look at the data, very often you get some interesting ideas which might be useful for oneself or other people to use as a starting basis for formulating hypotheses. And last time I had the honor of talking in this forum here, back in December 2022, this was one of my final graphs. I showed at that time how if you compare the sea surface temperature, this is a cartoon illustrating the oceans. Here we have the land area, 29%, 71%, 100%, and then we have the atmosphere here. And what I did was simply study satellite temperatures and lower troposphere, the global surface air temperature, and the global surface temperature from land areas only, the sea surface temperature, and the ocean temperature down to 200 meters. And in all cases, you found that what is important is the surface temperature of the ocean. That's the leading factor. The temperature at 200 meters in the ocean come with a delay of 20 months. The temperature in the lower troposphere are delayed with 2 months in relation to the sea surface temperature. The global surface air temperature is delayed with almost half a month in relation to the sea surface temperature, and the land surface temperature is delayed with about 2 months. So in all cases, what comes first is the sea surface, the ocean surface temperature. That's where the temperature signal peaks or the opposite is starting. And now, if I understand the CO2 hypothesis correctly, the temperature signal of increased CO2 should begin in the upper part of the troposphere. And if that was a dominant factor, I'm not saying that CO2 is not a greenhouse gas. I'm just saying that most likely the importance is not extremely big. This arrow should point the other way. But now clearly things are beginning at the sea surface. So the big question for science or climate interested science is actually, in my opinion, what controls the ocean surface temperature? And if I should come with a few guesses, it could be the sun, the solar insulation, it could be the cloud cover. And there might be other factors, but at least these two are candidates. So in this slide, I'm actually showing what I believe is really important to understand climatic variations. We have the atmosphere, the clouds, we have the sun, and we have the oceans. And the data are telling me that what controls the ocean surface temperature controls the global climate. So I would say, let me end with two conclusions and one suggestion. The first conclusion is that if you look at the observed data, it doesn't support the notion of an ongoing climate crisis. But the data shows a lot of interesting and partly recurring natural variations which should be studied. Second conclusion is that the ocean surface temperature appears to control the temperature in the atmosphere. And my suggestion for future research is simply that some educated people should really look into the details of what is controlling the ocean surface temperature. This was what I wanted to say. Thank you very much for your attention.